Hey guys, my name is Yusuf. I'm the Community and Academic Program Manager here at SimScale.
Hey guys, I'm Meg and I'm the Content Manager at SimScale.
Together, we do a podcast about engineering and our customers using SimScale for their simulation purposes.
We're here today with Jonathon Hunter Hill from SAV Systems. Jonathon, do you mind giving us a bit of a background of SAV Systems as well as like a background of you?
Oh yeah, thanks for having me. So I am the sector manager for education, SAV systems. Primarily for me, that means looking after our smart ventilation units called Airmaster. SAV as a whole is a sort of hybrid English-Danish company. So the way the business has built up over the years is that we have a lot of expertise primarily in heat networks, which is a technology that's been quite well perfected by the Danes. And then we've sort of expanded a bit into heat recovery ventilation. But typically the way we do things is we see how the Danes have done it with their decades of experience following the oil crisis back in the 70s. And we take their experience of low carbon technology, energy saving, that sort of thing. We try to implement it over here. So as a company, we've been involved in a number of sort of regulatory changes over the years. And yeah, for me, that involves a focus on schools, really.
Mm-hmm. So what I want to continue with is we have a nice quote from you, which I want to read now, and maybe you can comment on that, which is, I feel as an engineer, you don't just have an engineering obligation, but also a moral obligation to make sure children have good indoor air quality. It's not their choice to go to school, but it's our choice what quality of school environment we give them. Do you want to comment on that?
Yeah, sure. So I think it's easy as an engineer to say, okay, I've got these rules to work to, and I'll stick to them. And I think it's very easy as an engineer to be sort of boxed into that, or to box yourself in and say, these are my parameters. I'll just work within them and not consider outside them. So for me, I mean, that particular statement relates to the regulations we have for English schools or British schools. What guides mechanical engineers is BB 101. So it's Building Bulletin 101, and I think its full name is Guidelines on Ventilation, Thermal Comfort, and Indoor Air Quality in Schools. Mm-hmm. So that was re-released in 2018, and we were fortunate enough to be involved in that. It tries to the reason for the sort of reissue of it back in 2018 was that the previous version was in 2008. So in 10 years, the standard of buildings has changed quite a bit, and we have lots of buildings that are very well insulated, very airtight. And what's been happening is that you've got these really airtight buildings. There's no air change going on in those rooms. So older buildings normally are leaky. And so you've got air exchanging through the cracks in windows, that sort of thing, all the time. But newer buildings don't do that because any air leaving your building is probably going to carry heat with it, and therefore it's inefficient. So what was happening, you had all these really airtight classrooms, which have a really good sort of carbon footprint because you've got low heat loss. But the result was that you had very poor indoor air quality because there was no air exchange going on between inside and outside. Yeah. So BB 101 aimed to address this. What commonly happens in the UK is you just open the window if you need ventilation. And we've been doing that presumably forever, since windows first became a thing. But that's leading to drafts, and that's leading to lots of hot air just going straight out the window. So in the new BB 101, there was an aim to address this. What it says, though, and this is where my part where my quote comes in, is that if you have a natural ventilation system, you can have a 50% worse indoor air quality than a mechanically ventilated classroom. What that means is if you choose as an engineer to go for a naturally ventilated classroom, you're giving those children a worse learning environment. Mm-hmm. And we know through various bits of evidence that from going from 1,000 parts per million of CO2 in a classroom up to 1,500 parts per million of CO2 in a classroom has a dramatic effect on children's ability to learn. So as an engineer, in giving them that naturally ventilated classroom, you're potentially giving them less chance of success in their education. So as an engineer, you then have to weigh up, do I do the natural ventilation and give them worse indoor air quality and conceivably a worse education, or do I go mechanical and give them a better quality of education?
Yes,
And I'm very cynical of this document. It shouldn't have done that, which is where the moral thing comes in. If you use mechanical ventilation, you can also filter air that's coming into the room. So you're filtering out pollutants, which prevent children's lungs developing properly and have a long-term impact on their life. So that's really what I meant by that statement.
Get it.
So with that, what was really your motivation like for going into this line of work? Like, were you very morally motivated from a younger age, or was it something you kind of came across and then got really committed to helping, or what kind of was your motivation behind this?
I'm a problem solver generally. Quite frankly, I started working at SAV because the opportunity came along to work for a good company. But then over time, I think your views on the world change a bit, and the reality is we're going to have to reduce our carbon emissions. So for me now, the goal is working towards reduction in carbon emissions. So when people ask me, what does SAV do? My answer generally is we're a low carbon technology company. So for me now, the motivation is reducing carbon. And the UK government have set a target of virtually zero carbon emissions for the country by 2050. So for me and for the rest of the company, I feel that that's the target we're working towards. There's also a bit of motivation for me. I want to make a success of something, and that's the Airmaster, which is the smart mechanical ventilation that I look after.
Yeah, I see. Can you explain where CAE first came into play in your business?
As a business, we've always used CAD programs. That would be the first place where we had CAE. So for a long time, it was just AutoCAD, and people were producing building plans exclusively in AutoCAD, pretty much. That eventually expanded to involve BIM, so building information modeling, so having more advanced building models. Where we've got to now using CFD is that one of the criteria in BB 101 is that you have to avoid drafts in the classroom. And there's very specific temperature and velocity limits that you can have for your classrooms. And so for us using CFD software, it was about proving that we weren't going to cause drafts with our technology. And also highlighting, well, what we'd like to highlight for the industry is not only does natural ventilation not have filtered air, not only is it worse standard of indoor air quality, but it's also going to have a worse thermal comfort standard. Using mechanical ventilation, you can control all those things very well. So using CFD or CAE to do that, we were able to demonstrate the quality of control we have over the indoor environment.
Yeah.
Cool, that's awesome. So then what was you incorporated CFD after going through kind of like these other design evaluation tools? Like, what was your first experience, and like what were your first thoughts when you first did like your first CFD simulation?
My initial thoughts was, wow, we've got a lot to learn. We put in, it's that old thing of rubbish in, rubbish out. So initially it was, okay, we've put in what we think is right, and we've got results sort of consistent with that, but how do we make this accurate? So initially it was great to see, we were doing what we thought we were doing, what we'd intended to be doing. And then from that point on, it was, okay, how do we make this right? Because it's all well and good, a privately owned company putting out information to say we're really good at something. But that information then is subject to private interest. So we want to be able to open up to people to say, look, you can look at what we're doing, you can cross-examine it, and in doing so, we need it to be correct and accurate, and it needs to be honest. So that for us is where we've been trying to move it towards being as honest and as correct a setup as we can get.
Mm-hmm. What I would be interested in is, did you change your tools over time? Would you say that over your decades of experience, which you mentioned earlier on in the beginning of the podcast, did also your tools change during that time or time period, or how? Maybe you can explain that a bit in more detail.
I'm not that old.
Yeah, I know.
I've been working at SAV for 7 years, and I finished university in probably 2012.
Decades is a bit much, Joseph.
Yeah.
During the company. Yeah.
So as you see more intelligent tools going out in the marketplace, not necessarily ones that we use, but the availability of more intelligent tools, people want more intelligent results. So when I talked about the BIM software before, for example, if you could, I don't know how familiar you are with BIM models, but essentially you can map out the whole building and every piece of building service in that building. You could conceivably go even further and say, okay, it's a collaborative tool. We're already collaborating on the architecture, the civil engineering, the mechanical engineering, maybe even the interior design. Could we not analyze each of those rooms to say, what is their energy consumption? Is there going to be a draft? What are the comfort levels? That sort of thing. So, I mean, the evolution I'm seeing at the moment, it's just the level of intelligence in the models that we can create.
So with that, what would be your perfect workflow and perfect tool?
There are tools that go some way to do each of those things. So, for example, the BIM does a lot of mapping out stuff. There's software that we use. I don't know how globally or whether it's used in the rest of Europe or not, but there are tools that we use to model classroom energy consumption, that sort of thing. It'd be great if they all just work together, because one of the main advantages of that BIM modeling is the collaborative aspect. So someone could be working on one room and another person could be working on another, or redesigning a whole part of the building, and that is updated as people are working on it. So ideally, I think you'd be able to put all those tools into one super tool, I guess.
Maybe explain, because I saw on your homepage that the decentralization of energy is quite essential for you. Can you maybe comment on that? Just because it's quite interesting.
I think, okay, so it's not my expertise, but what you see often in the UK and where the regulations have been driving towards is saying that localized generation of carbon is a bad thing. Or what commonly happens is that you say, okay, in London, actual energy generation is reduced and therefore we've met a certain target. But what happens if you're doing that, if you're preventing decentralized energy generation, you're just putting it somewhere else. So you could say, okay, we've reduced our carbon footprint, but we're still buying some of our energy from France. So that France has some of our carbon footprint. That doesn't mean there's a reduced carbon footprint for the world. It just means it's somewhere else. And then if you are transporting electricity from France all the way to England, you're going to have huge losses, probably primarily sort of thermal losses in the wiring, for example, that would transport all that electricity. By decentralizing, you avoid all of that. So what we often do, one of our products is CHP, so combined heat and power. So essentially putting a small generator in a plant room that generates both heat and power at the same time. Mostly in the UK, at least, we generate power and the waste product is heat, but the CHP will harness that heat and distribute it. So if you decentralize that process, if you generate your electricity from within your building, you can then also use the heat, which is essentially free to use in that building. So by decentralizing it, you're making it a lot more efficient because you lose all the transmission, or you get rid of all the transmission losses. Someone else might give you a better explanation of that.
No, but that was very good, Jonathan. Thanks a lot. We also want to come back a little bit to CFD and the tool you use, namely SimScale.
Yes.
Surprise. Can you talk a little bit about SimScale, how you implement it into your workflow, and how easy was it to learn?
Sure. So the sort of adoption of SimScale for us was pretty simple. We decided that we wanted to demonstrate this draft-free air distribution in classrooms. That's primarily what we're using it for. We haven't expanded to anything else at this point. So from making that decision, it was a relatively simple process. I mean, from SimScale's perspective, I think there's a lot of hand-holding involved with us. So we went from having very limited. So in my team, there's another mechanical engineer, or there was at the time. We both had some CFD experience from university, but it was very different to using SimScale. So it wasn't that the platform was dramatically different. It was more that in university, when you're doing mechanical engineering, you're looking at things like brake discs, very small parts of things. So a classroom was a much bigger beast to contend with. So initially, like the first step, getting the building or the room to sort of mesh and the modeling involved in that wasn't too painful, I don't think. So we were able to export our BIM model from Revit, which is the software that we use for BIM modeling, directly into SimScale. And I think that was quite easy to do. Then getting from the initial meshing to the final product, that involved for us some support from some of the guys at SimScale, because frankly we didn't understand the process. It's not me that does the modeling now, but my colleague Megan, who does it, she has found over time that it's got very much easier. So I think there are a few fundamentals that she needs to understand initially, and now she does understand them. It's become a much simpler process. So yeah, the workflow has sort of smoothed out over time, and I think now it's been maybe 6 months of actual work on the designs here, on and off, and yeah, it's sort of become a lot easier over time to do that. And with SimScale being cloud-based as well, that's been really good for us, because we don't necessarily have the computing resources to be able to dedicate computers to doing CFD. One of the things we do now, for example, is offer it to our M&E consultants. So we say to them, if you'd like us to model a classroom, then we're happy to do that for you. And it takes the burden of, for them, it takes the burden away from them of having to model up a classroom, dedicate someone to do that, train that person if they need it, and then dedicate the whole computer to it. So from that perspective, it's been really good to sort of, I suppose it is, decentralize it for us, put the hard work somewhere else.
So when you do this, do you also then use SimScale to simulate thermal comfort for these models?
Yeah. So what we're primarily looking at when you're looking at draft is, when you're looking at draft, what you primarily look at is velocity and temperature. So through looking at all the different types of plots that are available to us, we've been able to see mainly, does it meet the criteria of BB 101? And that says things like, in a standard classroom, your delta T between air in the room and air entering the room should be no more than 2 degrees in a standard classroom. So what we've been able to do is look at the model in detail and take a load of cross sections and say, okay, we can see our airflow, we can see the occupied zone, what is the temperature difference? And then it's become for us a demonstrative tool to show to our consultants to say, look how we achieve this delta T, this is acceptable, that sort of thing.
Awesome. Yes, obviously you don't only do that, so ventilation design and so on, but you also have a lot of other things in your product line. Can you maybe talk about your product line in general and also how SimScale could be applied in the future for these kind of products?
So as I mentioned before, we do mostly heat networks. So if I give you a quick rundown of the products, CHP is one of them. So that's made by EC Power, Danish company. Then we have heat interface units, so they're called Danfoss flat stations. What heat interface units are, if you have a central plant room in a building, or you have a district heating scheme, you separate the district heating heat energy or water supply from what's actually in the flat. So you end up with, or the apartment, you have a heat exchanger in that apartment which separates the primary side from the secondary side. What that means is you're not bringing in dirty water from your plant side of things. You're only bringing in clean, fresh water from outside. So if you had a big district heating scheme in each of the flats in that building, or in each of the flats, maybe in each of the buildings in the scheme, you'd have a heat interface unit, which would allow you to transfer the energy between the two systems. So that is a huge product for us. That's probably our mainstay. And yeah, so I think we're the leading supplier of heat interface units in the UK, and we've certainly been at the forefront of driving that and driving district heating in the UK. We then have other technologies that link into that. So one of them is pressure compensated radiator valves. And quite honestly, I couldn't tell you enough about them and be convinced I was correct. So all I say is that they exist. They're actually pressure and temperature compensated. And that's as much as I know.
Excellent. But theoretically, you could apply SimScale for this kind of simulation.
Yeah, I think you could. Yeah, if that's what you'd like to do. So if you were designing those products, so if you were the one designing the radiator valves, for example, I think you could definitely be using CFD to achieve that and SimScale to achieve that. You want to know how your flow is being regulated and how, for example, the heat's being conducted in that product. So I could easily see it being used in that sort of application.
Excellent.
Okay, well, I think we're kind of ready to wrap up from our side. Do you have any other thoughts or anything you want to say about yourself or about SAV systems for the audience?
I mean, for me, if you're looking to decarbonize ventilation, you have to have a heat exchanger. That's really important. Doing heat recovery is going to be the only way we decarbonize our ventilation systems. And if we are going to live in environments where essentially the buildings are sealed, that's the only way you're going to be able to do it.
And with this, do you think that computer-aided engineering is like the only way to kind of improve this and innovate what we already have?
Yeah, I do actually. I think by using CAE, we're going to develop much better solutions. Certainly, in the way you distribute if you can distribute without having to use ductwork, diffuser grills, that sort of thing, you can dramatically cut energy consumption. And in achieving that, using CAE to work out how that flow will actually manage itself within a room, that it will be invaluable. Yeah. And it has been used in the past. We're in the development of our units, the current range, and there was certainly a lot of modeling that went on. And as we develop new generations of equipment, I don't doubt that we'll be, and also the sort of footprint of the technology reduces, as in the CAE technology. I think we'll see more and more of it. Yeah, thanks for your time today, and I'll speak to you soon, no doubt.
Thanks so much for being our guest.